You believe you are in one place right now. You are sitting somewhere, standing somewhere, existing at a single location in space. This seems like the most obvious fact about reality. When you look at your hand, it is here, not there. When you move, you go from one place to another place. You never experience being in two rooms at once. This is so deeply embedded in how you perceive the world that questioning it feels absurd, like questioning whether the ground is beneath your feet. But here is the problem. This obvious fact, this everyday experience of singular location, may not be how physical objects actually behave. And I do not mean this as a metaphor or as some vague spiritual notion or as a way of saying your attention is divided. I mean that the particles that make up your body right now may not have a single definite location. They may, in some precise physical sense, exist in multiple places simultaneously. Not because we lack information about where they are, but because the question, where exactly is this particle, may not have a single answer until something forces it to have one. This is not a guess. This is what decades of experiments tell us happens when we look carefully at how matter behaves. The person who helped us see this most clearly was Richard Feynman, and what he found was not a comfortable philosophical idea. It was a mathematical description that makes predictions, predictions that turn out to be correct to a precision that borders on absurd. So we need to understand what this actually means. Not the name of the idea, not the popular story, but what happens, what we observe, and what conclusions we are forced to accept if we take those observations seriously. If you want to see where this goes, what the experiments actually show and why it matters, stay with me. We're going to build this carefully. Here is what you can do in a laboratory. Take a source that emits electrons, one at a time. Not a beam, not a spray, but individual particles, separated in time. Point this source at a barrier that has two narrow slits cut into it. Behind the barrier, place a detection screen that records where each electron arrives. Now turn on the source and wait. The first electron hits the screen somewhere. Mark that location. The second electron hits somewhere else. Mark that location. Keep doing this. After one electron, you have one dot. After 10 electrons, you have 10 dots scattered across the screen. They appear random, unpredictable, but after thousands of electrons, something emerges. The dots are not distributed evenly. They form a pattern of bright bands and dark bands, stripes of high density and low density running parallel to the slits. This is an interference pattern. Now here is what matters. You sent the electrons one at a time. Each electron went through the apparatus alone. There was no other electron present to interact with. Yet the pattern that emerges is not the pattern you get when you fire bullets through two slits, or throw sand through two openings, or send any classical particle through a barrier. When you do that with ordinary objects, you get two bright patches on the screen, one behind each slit, with some overlap in the middle. But electrons do not do this. The pattern they produce has multiple bands, with regions directly behind the slits where almost no electrons arrive at all. Regions of darkness where you would expect brightness. This is not subtle. This is not a small quantum correction to classical behavior. This is a completely different pattern. And the pattern is precisely what you would get if you sent waves through two slits. Waves that spread out, pass through both openings, and then overlap on the other side, reinforcing in some places and cancelling in others. But you did not send waves, you sent particles, individual countable localized particles that arrive at the screen as single dots. So what exactly happened? Interference is what happens when two waves meet. If the peak of one wave arrives at the same place and time as the peak of another wave, they add together and you get a bigger wave. If the peak of one wave arrives at the same place as the trough of another wave, they subtract, and you get nothing, or nearly nothing. This is not mysterious. You can see it in water. Drop two stones in a pond and watch the ripples spread. Where the ripples cross, some regions have larger waves, some regions go nearly flat. That is interference. It requires that something be present in multiple locations at once so that it can overlap with itself. A water wave exists across a region of space. It has extent. So when it passes through two openings, part of it goes through one opening and part goes through the other, and then those parts meet and interfere. Now consider particles. A bullet fired at a wall with two holes in it goes through one hole or the other hole, never both. If you fire many bullets, some go left, some go right, and you get two piles of bullets on the far side. No interference, no banding, no regions where bullets refuse to land even though both holes are open. This is because a bullet is localized. It has a definite position at every moment. It travels along a single path. Its behavior does not depend on whether the other hole is open or closed. But the electrons do not behave this way. The pattern they produce depends on both slits being open. If you close one slit, the interference pattern disappears. The bands vanish. You get a single spread-out patch, as you would expect from particles passing through one opening. Open both slits again, and the bands return. This means that what happens at one slit affects what happens at the other slit. Even though you are sending one electron at a time, the electron is not splitting into pieces. When it arrives at the screen, it arrives whole, as a single dot, with the full charge and mass of an electron. Yet the probability of where it will arrive is determined by interference, as if something associated with that electron passed through both slits, spread out, overlapped with itself, and created regions of reinforcement and cancellation, not as if it randomly chose a slit, as if it went through both. This is not an interpretation. This is what the pattern requires. The mathematics of wave interference predicts exactly where the bright and dark bands will appear, and the electrons land accordingly with extraordinary precision. Feynman gave us a way to calculate where the electron will land, and the method is strange. You do not track the electron's position as it moves. You do not ask which path it took. Instead, you consider every possible path the electron could take from the source to the screen, not just the two paths through the slits. Every path. Paths that curve wildly through space. Paths that loop backward. Paths that spiral. Paths that seem absurd. Each path gets assigned a number, which Feynman called a probability amplitude. This is not the probability itself. It is something you calculate that will give you the probability, but it behaves differently. Amplitudes can be positive or negative, or more precisely, they are complex numbers that have both magnitude and direction in an abstract mathematical space. Here is what you do. You add up the amplitudes for all possible paths, not just the likely paths, all of them. When you add these amplitudes, something remarkable happens. Some amplitudes point in similar directions and reinforce each other. Others point in opposite directions and cancel each other out. After you add them all together, you get a final amplitude for the electron arriving at a particular location on the screen. Then and only then, you calculate the probability by taking the square of that final amplitude's magnitude. Where the final amplitude is large, the probability is high and electrons land frequently. Where the final amplitude is small or zero, the probability is low and electrons rarely or never land. This method works. It predicts the interference pattern exactly. It predicts where the bright bands will be, where the dark bands will be, how wide they will be, how their spacing depends on the distance between the slits and the wavelength associated with the electron's momentum. The agreement between prediction and experiment is not approximate. It is exact, within the limits of measurement. But notice what this method does not include. It does not say the electron took one path. It does not say the electron took all paths. It says that to calculate where the electron will land, you must include every possible path in your calculation, and these paths interfere with each other through their amplitudes. The electron does not have a definite trajectory. The question, which path did it take, does not have an answer that you extract from this mathematics. The mathematics works by not answering that question. Now you might think, I will simply watch. I will place a detector at each slit to determine which slit the electron actually passes through. This is not a thought experiment. This has been done. You put a measuring device near the slits, something that can tell you whether an electron went through the left slit or the right slit without destroying the electron. Perhaps you shine light on the slits and watch for scattered photons, or use some other method that registers the electron's presence. And it works. The detector clicks. It tells you this electron went through the left slit, the next electron, right slit, the next, left slit. You now have definite information. Each electron took a definite path. But when you look at the screen after collecting thousands of electrons, the interference pattern is gone, completely gone. What you see now is exactly what you would expect from classical particles. Two bright patches, one behind each slit, with some overlap in the middle, no bands, no regions of destructive interference, no places where electrons refuse to land despite both slits being open. The act of determining which slit the electron passed through destroyed the interference. This is not because you disturbed the electron too much, though early explanations sometimes suggested this. You can make the measurement arbitrarily gentle. You can use methods that barely interact with the electron. It does not matter. As long as the information about which path the electron took exists, even if you do not look at it, even if you erase it later without reading it, the interference pattern does not appear. What matters is whether the which path information is physically present in the universe, encoded in some detector, some measurement device, some environmental interaction. If it is, the electron behaves as though it went through one slit. If it is not, the electron behaves as though it went through both. You cannot have both. You cannot preserve interference and know which path was taken. This is not a limitation of our equipment. This is not a temporary gap in knowledge that better technology will close. This is a feature of how the world works. The mathematics tells you this. When which path information exists, the amplitudes for the two paths do not interfere. They add in a different way, a way that produces classical probabilities, not quantum interference. When which path information does not exist, the amplitudes interfere and you get the banded pattern. Feynman's method accounts for this. When the electron's path is measured, you do not sum over all paths. You sum only over paths consistent with the measurement result. The interference between paths going through different slits disappears from the calculation, and so it disappears from the observed pattern. The world responds to what is determined, not to what you personally know. The electron does not have a path until something forces it to have one, and once it has a path, it stops behaving like something that exists in multiple places. You are made of particles, electrons, protons, neutrons. These are the same electrons that produce interference patterns. So if an electron does not have a definite location until something measures it, why do you have a definite location? Why are you not smeared across multiple places, existing in a superposition of sitting and standing, here and there? The answer is not that quantum mechanics stops applying at some size. There is no line where objects become too big for quantum behavior. The answer is measurement, but we need to be precise about what measurement means. It does not mean conscious observation. It does not require a human or a mind. Measurement, in the physical sense, means interaction with the environment in a way that leaves a record, a mark, something that distinguishes one outcome from another. You are constantly interacting with your environment. Photons from the room bounce off your skin. Air molecules collide with you. The chair you sit on presses against you. Each of these interactions is a measurement. Each one entangles you with the environment, creating which path information about your location. The interference between different positions is destroyed not by your awareness, but by the irreversible physical records left in the surrounding world. A single electron in isolation can maintain a superposition because it is small and weakly coupled to its environment. It does not scatter many photons. It does not displace much air. It can travel through an experimental apparatus without leaving a trail. But you displace trillions of air molecules every second. You radiate heat. You reflect light. Every one of these interactions is like placing a detector at one of the slits. The environment measures your position constantly, and this measurement forces you to have a definite location. This process is called decoherence, and it happens extraordinarily fast for macroscopic objects. For something the size of a dust grain in air, superposition is destroyed in less than a microsecond. For something the size of a human, it would be destroyed in a time so short we do not have good language for it, something like 10 to the negative 40 seconds. So you do not experience being in two places because the world around you will not let you remain in two places. The mathematics of quantum mechanics still applies to you. The amplitudes still exist. The path integral still includes every possible configuration of your particles. But the interference terms, the terms that would allow you to notice being in a superposition, are wiped out essentially instantly by your interaction with the environment. This is not a failure of quantum mechanics. This is quantum mechanics correctly predicting that large, warm, complex objects interacting with many particles will behave classically. You exist in multiple places in the mathematics. The amplitudes for different configurations are all present in the calculation. But the observable consequences of this, the interference effects, are suppressed by decoherence to a degree so extreme that classical physics emerges as an excellent approximation. Here is what we cannot escape. The interference pattern appears when we do not measure which slit the electron passes through. It disappears when we do measure. This has been tested thousands of times in variations so careful and controlled that arguments about experimental error are not serious. The pattern is real. The dependence on measurement is real. And no one has found a way to explain this by saying the electrons simply had a definite position all along that we just did not know. That explanation fails because of a specific quantitative fact. If the electron had a definite but unknown position, if it really went through only one slit, and we simply lacked information about which one, then the statistics would be different. You would get classical probability. Sometimes the electron goes left, sometimes right. You add up those two possibilities, and you get two bright patches with overlap. But that is not what happens. The quantum prediction is different from the classical prediction in precise, measurable ways. There are places on the screen where the classical calculation says electrons should land, where both slits being open should increase the probability, and yet electrons never land there. Places where opening the second slit makes it less likely, not more likely, for an electron to arrive at a particular spot. This is interference. This is what happens when amplitudes cancel, and you cannot get cancellation from classical probabilities. Probabilities are always positive. They add, they do not subtract. Amplitudes can point in opposite directions. They can cancel. This is not a subtle distinction. The interference pattern has bright and dark fringes. If you cover one slit, the dark fringes disappear and some of them become bright. Opening a second path made it less likely for the electron to reach certain locations. That is not something classical thinking can accommodate. You cannot make something less likely by giving it more options unless something wave-like is passing through both options and interfering with itself. So either the electron or something associated with the electron, or the amplitude that describes the electron, or however you want to phrase it, must involve both slits, not in a vague, hand-wavy sense, in a precise sense that shows up in the calculation and matches the experiment. Feynman's path integral gives you a method. Sum over all paths, let the amplitudes interfere, calculate probabilities from the result. This is not an interpretation grafted onto the mathematics. This is the mathematics. The path integral formulation does not include a term for the actual path the particle took. It includes all paths. You might say this is just a calculational trick, a way of getting the right answer without claiming the electron literally takes all paths. Fine. But then you need to explain why this trick works. Why does nature conform to a calculation that includes configurations the particle supposedly never occupies? Why does the answer depend on summing over paths through both slits if the electron really went through only one? The mathematics resists the story we want to tell. Feynman did not like interpretations. He did not like stories that went beyond what could be calculated and tested. When people asked him what the electron really does, he would often say, "It does what the mathematics says it does, and the mathematics says you calculate amplitudes for all possibilities and add them." If you ask whether the electron goes through one slit or both slits, you're asking the wrong kind of question. The question assumes the electron has a definite trajectory, a property called a classical path, and nothing in the mathematical formalism requires this property to exist. The formalism works without it. The formalism, in fact, works by not assigning it. You might feel unsatisfied by this. You might want to know what is really happening. But Feynman would push back on that desire. What does really happening mean? It means you have some picture in your mind, some model built from everyday experience, and you want the electron to fit that model. You want it to be a little ball that travels along a line. But everyday experience is built from interactions with large objects in environments full of decoherence. Your intuition is a guide to how trillions of particles behave when constantly measured by their surroundings. It is not necessarily a guide to how a single particle behaves in isolation. The electron is not hiding its true path from you. It does not have a true path in the sense you mean. What it has is an amplitude, a quantum state, a mathematical object that evolves according to precise rules and gives correct predictions when you ask calculable questions. Where will the electron land? The mathematics answers. With what probability? The mathematics answers. Did it go through the left slit? The mathematics says, this question has no answer unless you measured it. And if you measured it, the pattern changes. And the mathematics predicts that too. This is not ignorance. This is the structure of the theory. And the theory works. It works for electrons. It works for atoms. It works for photons. It works for molecules large enough to see under a microscope. Interference has been demonstrated with objects containing hundreds of atoms. The pattern persists. The dependence on measurement persists. The quantum predictions remain correct. At some point, you have to take seriously the possibility that your demand for a classical picture is the problem, not the theory's refusal to provide one. Nature is not obligated to behave in a way that matches your intuition. Your intuition was built by evolution to handle objects at human scales, where decoherence is so overwhelming that quantum effects are invisible. It was not built to handle isolated particles. So when Feynman said the electron exists in multiple places, he did not mean it in a mystical sense. He meant that the mathematical object describing the electron, the amplitude, is a function of position, and this function is non-zero in multiple places. When you calculate observable predictions, you must account for the amplitude at all those places. You cannot ignore the amplitude at one slit and get the right answer. Both contribute, both interfere. The prediction depends on both. In that precise operational sense, the electron is in multiple places, not because it has multiple positions simultaneously in some metaphysical way, but because position, as a definite single-valued property, is not something the electron has until a measurement forces it to have one. Before measurement, there is only the amplitude, and the amplitude spreads. We're almost at the end. Let me tell you what we actually know, what remains uncertain, and why none of this should comfort you. If this is how particles work, and you are made of particles, then the question is not whether quantum mechanics applies to you. It does. The question is why you do not notice, and we have already answered this. Decoherence. Your particles are measured constantly by the environment, but this raises something uncomfortable. There was a time, very early in the universe, when particles were not constantly measured. When the universe was hot and dense, particles were colliding frequently. Yes, but in certain configurations, under certain conditions, quantum coherence could be maintained across surprisingly large scales. The early universe was, in some sense, more quantum than the world you see now. And even now, in carefully controlled experiments, we can isolate systems from their environment and watch quantum behavior emerge at scales that seem absurd. Molecules with hundreds of atoms producing interference patterns, superconducting circuits, large enough to see with the naked eye, existing in superpositions of different current states. These are not thought experiments. These are performed experiments with results that match quantum predictions. So the division between the quantum world and the classical world is not a division of size or complexity. It is a division of isolation. A system behaves quantum mechanically when it is sufficiently isolated from measurement by its environment. It behaves classically when it is not. You are not isolated, but your particles, considered individually, still obey quantum rules. The amplitudes for different configurations of your atoms are still present in the full quantum state of the universe. It is just that these amplitudes do not interfere in any measurable way, because decoherence has separated them into branches that no longer interact. This leads to the many worlds interpretation, though we need to be careful here. Feynman himself did not advocate strongly for any interpretation, But the mathematics he worked with is compatible with the idea that all the amplitudes are real, that every possible outcome occurs in some branch of the wave function, and that what we call measurement is simply the process by which we, as physical systems, become correlated with one branch and lose coherence with the others. You do not see the other branches because you are part of a branch. The version of you in this branch only has access to the outcomes in this branch, but the amplitudes corresponding to other outcomes are still there in the mathematics, still evolving, still part of the full quantum state, whether you call this many worlds or simply the wave function evolving unitarily without collapse is a matter of language. The mathematics is the same. And the mathematics says that when you perform a measurement, the part of the wave function corresponding to different outcomes does not disappear. It simply decoheres from your branch. Other interpretations exist. The Copenhagen interpretation says the wave function collapses upon measurement and only one outcome becomes real. Pilot wave theories say particles have definite positions all along, guided by a non-local wave. These interpretations make the same predictions for almost all experiments, which is why the debate continues. But what we cannot do is pretend quantum mechanics is just a useful fiction. It makes predictions that differ from classical mechanics. Those predictions are tested, they are correct. Something genuinely strange is happening. Either particles do not have definite positions until measured, or they have positions but are guided by non-local waves, or all outcomes occur in parallel branches. Pick your strangeness, but you must pick one. The classical picture where things simply have properties independent of measurement does not work.